Hello, my name is Adam Hartman, and today I will be presenting my term project on additive manufacturing used in molding, casting, and forming. As an overview, my presentation will cover the following topics: a brief description of the additive manufacturing techniques, and then how is additive manufacturing applied to plastic injection molding, metal casting, and sheet metal forming. Then I'll look at some of the findings from the survey of literature that I completed and the conclusions that I drew from that survey. There are 7 types of additive manufacturing, or 7 categories rather, that are identified by the ASTM standard listed below. Those 7 types are binder jetting, which is a powdered material that is then has liquid binder or glue sprayed onto it layer by layer. Directed energy deposition, which usually has a welding or metal powder sprayed at a surface with laser or electrical energy used to locally melt the material. Material extrusion, which typically melts polymers and squeezes them out of a nozzle layer by layer. Material jetting, which is similar to binder jetting, except the material itself is put down layer by layer. Powder bed fusion, where powdered materials, including ceramics, metals, and polymers, are melted by laser energy in a layer by layer fashion. Sheet lamination, where individual sheets of material are cut out, usually with laser or with CNC blades, and then heat pressed together to build up layers. And vat polymerization, where specific light sensitive resins are exposed to laser light, and that's how the layers are built up. 2 applications of additive manufacturing for plastic injection molding are shown here. The first on the right is vat polymerization, where high temperature resins are cured by laser light layer by layer and end up making molds that are actually high enough temperature to resist the temperatures and pressures used in molding certain plastics. Another application in injection molding is for directed energy deposition, which can actually form tool steel and enables conformal cooling channels inside of tools that can efficiently remove heat during the molding process, and also can repair damaged tools that may be damaged over time. Here I'm showing 2 applications of additive manufacturing for metal casting. On the right is binder jetting of actual mold sand that enables us to make novel sprues or other features such as undercuts that aren't available in traditional sand casting. And in the bottom, we have material extrusion or vat polymerization, where models of the intended part are made and then used in investment casting and burnt or melted out during the metal casting process. Additive manufacturing can also be applied to sheet metal forming. In the bottom, I'm showing how the material extrusion of ABS can be used to make functional plastic dies and punches for use on certain sheet metals. In the center, I'm showing how powder bed fusion can be used to make topology optimized tool steel, where mass is removed but stiffness is retained. And on the far right, I'm showing how vat polymerization can be used to make a model of an intended punch design, and that model can be cast in resin, cured, and then used in a traditional sheet metal forming operation. Through the literature that I surveyed, these were my findings. I looked at 48 articles and found that powder bed fusion was the most common technique across all the different manufacturing procedures that I looked at, and that directed energy deposition had the least amount of representation. Binder jetting was almost exclusively used in metal casting, and it's in fact a very popular technique that's used commercially today. The most frequently mentioned strengths by authors were fast tooling, followed by low cost of the tooling made, and then finally unique features that were available only due to additive manufacturing. The most frequently mentioned drawbacks were that the surface quality of the tools were poor, they had a short lifetime, and the thermal performance was poor. Based on the review of literature, here are my conclusions for additive manufacturing and tooling. Additive manufacturing and tooling has been a steeply growing area of research over the last 10 years. The fact that additive manufacturing enables low cost and quick iterations means that researchers are able to try out new techniques and applications quickly in their labs. And the ability for additive manufacturing to generate unique features that are closely coupled to simulation means that both researchers and designers can optimize the cost, mass, time, and performance of not only their tools, but also the parts that come out of them.